All right, welcome back to the deep dive. So today we are going to be tackling like a seriously huge subject, the entire history of the universe. You guys sent us these excerpts from a YouTube video transcript called How Did the Universe Begin? It's from the channel History of the Universe, and I think we are ready to jump right in.
Yeah, it's definitely quite a journey. We're going from like the very, very beginning of the universe to the present day, exploring all of these crazy ideas and incredible discoveries that we've made.
Yeah, and so the video starts with like a very fundamental question, right, that humans have been asking for centuries. How did it all begin? Of course, the video jumps into the Big Bang Theory, which I think is like the leading scientific explanation right now.
Yeah, for sure. The Big Bang basically proposes that the universe came from like this extremely hot, extremely dense state, like 13.8 billion years ago. It's a pretty strong theory that explains, a lot of what we see.
Yeah, it makes a lot of sense. But it's not the only idea out there, is it? The video also goes into some alternative theories.
Oh, yeah. There's some really interesting ones. There's this concept that the universe might be infinite, like it's always existed. It's just, maybe becoming less dense over time. Just imagine that a universe with no beginning and no end.
Whoa, that's crazy. The video also mentions some other really interesting ideas like the Big Bounce, where the universe, it kind of cycles through like periods of expansion and contraction, almost like a cosmic heartbeat.
The Big Bounce, yeah. That's a cool one. Then there's also the multiverse theory, where our universe is just like one of many universes, right? Each one with its own like unique properties and laws of physics.
Whoa, that's getting into some serious mind-bending stuff now. It's almost like science fiction.
Yeah, definitely. And then the video even goes into like string theory, which suggests that our universe might have actually formed from like a collision between these higher dimensional things called brains.
Okay, hold on. Brains. What are those?
So imagine brains as these membranes or surfaces, but instead of existing in like our normal 3D space, they exist in these higher dimensions. Like think about our entire universe as a 3D brain floating in a space with many more dimensions. And in string theory, these brains can, interact with each other, they can collide. And it's thought that maybe that collision is what sparked the creation of our universe.
Oh, okay. That's a lot to think about. But I really love how this deep dive is already kind of challenging.
Yeah, I think it's a good reminder that, science is all about constantly questioning and exploring, even when it gets super weird. And speaking of weird, let's maybe switch gears and talk about temperature.
All right, bring on the heat. The video mentioned this really surprising fact that the highest temperature ever recorded, it wasn't in a star, it was actually here on Earth.
Yeah, that's right. At CERN, they have the Large Hadron Collider. Scientists there, they smashed these lead atoms together and they created a temperature of like, get this, 5.5 trillion degrees Celsius. That's like 50 times hotter than a supernova.
Wow, that's incredible. But even that like mind-blowingly high temperature, it's still tiny compared to the theoretical like upper limit, right? The Planck temperature.
Oh yeah, the Planck temperature, that's a whole other level of crazy. Something like 1.4 times 10 to the power of 32 Kelvin. It's just this massive number that's, impossible to really comprehend.
Yeah.
And it's thought to be the temperature that existed during the very, very first moments of the universe, what we call the Planck era.
Okay, so the Planck era, that's like the beginning of the universe, right? Tell me more about it.
Yeah. So the Planck era, we're talking about the first 10 to the power of negative 43 seconds after the Big Bang. I mean, to put that into perspective, if you stretch 1 second out to be as long as the entire age of the universe, the Planck era would be shorter than a billionth of a billionth of a billionth of a second.
Wow. That's unimaginably small. So what was actually happening during this like incredibly short but like super important time period?
Well, basically, the universe was just unbelievably small and dense, like crammed into a space even smaller than a single proton. And at these scales, you've got both quantum mechanics, which is like the rules for how tiny things behave, and you've got general relativity, which describes gravity, both trying to work at the same time.
But wait, don't those two theories like clash? Like they don't really work together, do they?
That's exactly the problem.
Right.
Our two best theories for explaining the universe just totally incompatible at these crazy high energies and densities. This conflict between quantum mechanics and general relativity during the Planck era, it's one of the biggest mysteries in physics right now.
It's like trying to force two completely different puzzle pieces together. How are scientists even trying to solve that puzzle?
So there are a couple of interesting ideas. One involves these hypothetical particles called gravitons, which would basically carry the force of gravity, much like photons carry light. And then there's another approach called loop quantum gravity, which suggests that space-time itself, like the fabric of reality, isn't actually smooth and continuous. It might be made up of these tiny, like granular pieces.
So it's almost like saying reality itself is like pixelated, made up of these tiny little chunks. That's wild. I mean, it's just amazing to think about like the very fabric of space and time, having this fundamental structure.
It's definitely mind-blowing stuff. So moving on from the Planck era, let's dive into the idea of force unification.
Okay, this is where the video brings up that spinning coin analogy, right?
Yeah, exactly. Picture a coin spinning so fast that you can't even tell if it's heads or tails. It's just this blur. Well, in a similar way, at these super high energies, like what you'd find in the early universe, the fundamental forces of nature, the strong force, the weak force, the electromagnetic force, they all basically blend together and they act as a single unified force.
So it's like the forces haven't really separated yet. They're all just kind of rolled into one big force.
Yeah, that's a great way to put it. But then as the universe expanded and it started to cool down, these forces began to separate, much like if that spinning coin starts to slow down and you can finally see, oh, it's heads or it's tails.
So the separation of forces, it happened during like specific periods in the early universe, right?
Exactly. So first you have the grand unification epoch, which is where the strong force split off from this, what we call electroweak force, which is the electromagnetic and weak forces still combined. And then as the universe cooled even further, we get to the electroweak epoch, where the electromagnetic and weak forces finally split apart. And that leaves us with the four distinct forces that we see today.
Okay, so we've got the Planck era where all the forces are together,
right.
Then the grand unification epoch where the strong force breaks away, and then the electroweak epoch where the electromagnetic and weak forces go their separate ways. The universe is really starting to take shape. So what happens next?
Well, next up is something that really revolutionized our understanding of the early universe, inflation. So inflation, it's this idea that for just like a tiny, tiny fraction of a second after the Big Bang, the universe, it expanded unbelievably fast, like way faster than the speed of light. It sounds pretty wild, but this idea actually helps explain some things about the universe that the Big Bang theory on its own, it just couldn't really explain.
Okay, yeah, I'm curious. What were those things? I remember the video mentioned a few, like the horizon problem and the flatness problem and something about magnetic monopoles.
Yeah. So the horizon problem, it basically asks, like, why are these really distant parts of the universe that should never been in contact with each other, why do they have almost the same temperature? It's like, imagine you have 2 cups of coffee and they're brewed like miles apart, but they somehow end up at the exact same temperature.
Okay, yeah, that is pretty strange. So how does inflation explain that?
Okay, so imagine that those 2 cups of coffee, they were actually like right next to each other at the beginning, so they could easily reach the same temperature. And then picture them being like super quickly pulled apart so they end up miles away.
Yeah.
That's basically what happened during inflation. All those regions of the universe that we see today, they were once like super close together so they could reach a uniform temperature, and then boom, inflation flings them apart.
Okay, that's actually a pretty cool explanation. What about the flatness problem?
So the flatness problem, it comes from the fact that the universe, it looks really, really flat. It's kind of like if you take a balloon and you blow it up to like a gigantic size.
Yeah.
The surface of that balloon, it gets flatter and flatter the bigger it gets. In the same way, that super fast expansion during inflation, it basically stretched out the universe so much that any kind of bumps or curves that it might have had at the beginning, they just got completely smoothed out.
Yeah.
And that's why we see it as flat today.
So inflation basically like ironed out any wrinkles in the universe.
Yeah, exactly. And then you've got those missing magnetic monopoles. These are these hypothetical particles. And they're supposed to have only one magnetic pole, like either north or south. And some theories say they should have been all over the early universe, but we haven't actually found any.
Yeah, the video compared it to like baking a cake, expecting it to be full of chocolate chips, but then you cut it open and there's none.
Yeah, it's a great analogy. So inflation, it explains this missing ingredient by saying that any magnetic monopoles that might have been created, they would have been spread out so thinly by that super fast expansion that it'd be almost impossible to find them now.
Okay, so inflation, it solves all of these problems, which is awesome, but like what actually caused this super fast expansion to even happen in the first place?
Well, the exact mechanism that kicked off inflation is still a bit of a mystery, but a lot of physicists think that it involves this hypothetical field called the inflaton field. You can think of it's like this energy field that was all throughout the early universe, and it was like this fuel that drove that crazy expansion. And then as the inflaton field decayed, it would released all of its energy, reheating the universe, and that gave rise to all the particles that we see today.
So it was kind of like a cosmic fuel tank powering the universe's like growth spurt.
Yeah, that's a great way to put it. Okay, so we've talked about the universe expanding like crazy, but now let's switch gears a little bit and talk about how particles actually got their mass, which has to do with these really interesting ideas of symmetry breaking and the Higgs field.
Yeah, the video talked about how symmetry is important in physics, but then it actually needs to break down for our universe to form the way we know it. It's like this weird paradox.
Right. So in physics, when we talk about symmetry, we mean something that stays the same, even when other things change. Like the laws of physics are symmetrical. They work the same way here on Earth as they do in a galaxy far, far away. But for our universe to develop all of the different particles and forces that we see, that initial symmetry, it had to be broken.
So how did that happen? How did symmetry break down? The video used this analogy with a ball of dough, I remember.
Right. Imagine you have this perfectly smooth ball of dough. It's symmetrical, looks the same from all sides. But to make bread, a good loaf of bread, you need to knead it, you got to stretch it, you have to basically break that initial symmetry. Well, something kind of similar happened in the early universe. As the universe cooled down, it went through these changes, these phase transitions, kind of like how water changes from a gas to a liquid to ice. And each of those transitions, it broke some of that initial symmetry, and that led to the different forces and particles that we see.
So as the universe cooled, its perfect symmetry, it shattered, and that's how we grew all this complexity. That's amazing. But how did that symmetry breaking actually lead to particles having mass?
Yeah, that's where the Higgs field comes in. Imagine a cocktail party, right?
Yeah.
If you're just some random guest, you can move around pretty easily.
Yeah.
But if you're like a celebrity, people are going to crowd around you, it's going to be harder to move.
Oh, yeah, that's that cocktail party analogy.
Exactly. So in this analogy, the partygoers, they represent the Higgs field, and the celebrity, that's a particle. The more the Higgs field interacts with a particle, the more resistance that particle feels, and that resistance is what we experience as mass.
So the Higgs field is like cosmic molasses slowing down certain particles and giving them mass.
That's a great way to think about it.
Oh.
And the Higgs boson, which, scientists discovered back in 2012, that's like the ripple of excitement that goes through the crowd when that celebrity walks in.
So the Higgs boson, it confirms that the Higgs field is real, and it helps explain how particles get their mass. That's so cool. It's amazing how these really abstract concepts have such a huge impact on the universe
Yeah, totally. All right, so now we've got particles with mass. Let's move on to the quark era, which started about a millionth of a second after the Big Bang. The universe had cooled down enough for quarks, which are like the little building blocks of protons and neutrons. They could finally start sticking together.
Oh yeah, quarks, those tiny little particles, they're like the Lego bricks of matter. But the video mentioned something surprising about protons, right? Most of their mass doesn't actually come from the quarks themselves.
That's right. It turns out that most of a proton's mass actually comes from the energy of those strong force interactions that are happening between the quark, and also from the gluons, which are these particles that carry the strong force. Remember Einstein's famous equation, EMC2? It basically says that energy and mass, they're like two sides of the same coin.
So a big chunk of the mass that we experience in our everyday lives, it's actually a form of energy that's locked up inside protons and neutrons. Whoa.
Yeah, pretty mind-blowing, right? And this actually leads to another really interesting question. Why is there more matter than antimatter in the universe?
Yeah, I remember the video talked about the possibility of an alien civilization that accidentally wiped itself out with antimatter weapons. Well, that's a pretty scary thought. What's the real scientific explanation for why there's this imbalance?
So the idea is that in the early universe, matter and antimatter, they should have been created in equal amount. And when matter and antimatter meet, they annihilate each other, releasing a burst of energy.
So if matter and antimatter were created equally, they should have just canceled each other out completely, leaving nothing but a sea of energy?
Exactly. But luckily for us, something happened that tipped the scales in favor of matter. That's why we're here. And the key to this imbalance might be something called CP violation. It's this violation of a fundamental symmetry in particle physics. And it suggests that matter and antimatter, while they're almost identical, they actually behave a little bit differently in certain interactions, especially those that involve the weak force. And this tiny difference, it could have led to a slight excess of matter over antimatter in the early universe.
So this tiny little asymmetry in the laws of physics, it had a huge impact on the fate of the universe. Without it, we wouldn't have galaxies, stars, planets, or even us.
You got it. Okay, let's shift gears again and talk about neutrinos, these super elusive ghost particles that almost never interact with matter.
The video called them ghosts because trillions of them pass through our bodies every second, but we don't even notice them. It's they're in a completely different dimension or something.
Yeah, that's a good way to put it. But even though they're super hard to detect, neutrinos can tell us a lot about the history of the universe because they were some of the very first particles to break free from that super dense soup of the early universe, just like a second after the Big Bang. Scientists are actually searching for this, what they call relic neutrino background, kind of like the cosmic microwave background, that would give us a glimpse of the universe when it was only a second old.
It's like we'd be looking back in time to when the universe was a baby. The video also mentioned that neutrinos can help us study these really extreme events in space, like supernovae, right? How does that work?
So because neutrinos can basically pass through anything, they can give us this unique view of events that are just too dense or too great for us to see with light. They're like these little messengers carrying information from the hearts of exploding stars and other crazy stuff happening in the universe.
Okay, before we move on, I want to touch on those mysterious primordial black holes. The video suggested that they might explain how these supermassive black holes that seem to have formed way too early in the universe, how they got there.
Yeah, so supermassive black holes, these are black holes that are millions or even billions of times the mass of our sun. And we find them at the center of most galaxies, including our own Milky Way. And we think they formed from the collapse of giant stars. But the thing is, we found these supermassive black holes that were around just a few 100 million years after the Big Bang, way before there were even enough stars to create them through that normal process.
That's like finding a skyscraper in a place where people are just starting to build, like, small houses.
Yeah, exactly. So the fact that these early supermassive black holes exist, it suggests that there must be some other way that they formed. And one idea is that they actually formed directly from these dense spots in the very, very early universe, skipping the whole star collapse thing entirely.
Yeah.
These primordial black holes, they would have been like these seeds that quickly grew into the supermassive black holes that we see today.
So they were like cosmic fast trackers making supermassive black holes way fast.
Exactly. And scientists are looking for evidence of these primordial black holes. They're using all sorts of techniques, like looking for these things called microlensing events, where a primordial black hole passes in front of a distant star and makes it briefly brighter. And they're also looking for gravitational waves that could have been created when two primordial black holes collided.
Man, this deep dive is taking us on a wild ride. What's next on our cosmic adventure?
Okay, so now let's explore how those first elements were created in the early universe through this process called Big Bang nucleosynthesis.
All right, so let's talk about how the universe actually made those first elements. I remember the video mentioned a big scientific breakthrough with nuclear fusion, right?
Yeah, you're probably thinking about that experiment at the National Ignition Facility back in December 2022, where they managed to, for the first time ever, create this fusion reaction that actually produced more energy than it took to start it. It was a really big deal.
Yeah, it was huge news. And they did that by using like these super powerful lasers to basically force these hydrogen isotopes to fuse together, which releases a ton of energy. That's kind of similar to what happens inside stars, isn't it?
Yeah, you can think of stars as these giant fusion reactors. But there's a bit of a difference. Stars mostly fuse hydrogen nuclei into helium, while that experiment they use heavier isotopes of hydrogen, deuterium, and tritium.
Oh, okay. So where did those heavier hydrogen isotopes come from?
That's where Big Bang nucleosynthesis comes in.
Yeah.
This is the process that created the first elements, like hydrogen, helium, and a tiny bit of lithium, just a few minutes after the Big Bang.
So this elemental cooking happened before stars even existed.
Exactly. Imagine the universe, like 1 minute after the Big Bang. It's still crazy hot, super dense, but it's cooled down just enough for protons and neutrons to start sticking together. But there was this bottleneck in the process.
A bottleneck? What do you mean?
Well, to make helium, you first got to create deuterium, which is a hydrogen nucleus with an extra neutron. But the universe back then, it was so energetic that any deuterium that formed, it just got immediately blasted apart by these high-energy photons.
So it's kind of like trying to build a sandcastle on a beach, but the waves keep crashing in and washing it away.
Yeah, perfect analogy. So it wasn't until like 3 minutes after the Big Bang, when the universe had cooled down a bit more, that deuterium could finally stick around long enough to fuse into helium.
So the universe needed to hit this like sweet spot temperature for this whole elemental cooking thing to actually work.
Right. And it's actually amazing how much helium was created in just those few minutes. Like the amount of helium we see in the universe today, about 25% of all the matter, it's strong evidence that backs up this whole Big Bang nucleosynthesis idea.
Okay, so we've got hydrogen, helium, a sprinkle of lithium. What about all the other elements? Where did those come from?
Those were made much later, inside stars, and during these giant explosions called supernovae, so heavier elements like carbon, oxygen, iron, all that stuff. They were created by fusing those lighter elements together inside those super hot and dense cores of stars. And then when those massive stars die, they explode as supernovae, and they scatter all these newly created elements out into space. And that's how the universe got enriched with all the ingredients needed to make planets and eventually life.
So basically, every element in our bodies, it can be traced back to those first few minutes after the Big Bang, and then later on to those stars that created all the heavier stuff. It's like this incredible cosmic connection.
It really shows how interconnected everything in the universe is. And speaking of connections, the video goes on to explore how those building blocks of life, how they might have emerged.
Yeah, that part was fascinating. They talked about how scientists have found these organic molecules in space, like alcohols, acids, and even nucleobases, which are the building blocks of DNA and RNA. They found them in these interstellar clouds and even in meteorites.
Yeah, and those discoveries suggest that the basic ingredients for life, they might have actually been delivered to Earth from space.
Like some kind of cosmic delivery service. But the video really focused in on this one particular molecule, helium hydride. They said it was the very first molecule to form in the universe, right?
Yeah, helium hydride. And it was just recently detected in this planetary nebula, which is this cloud of gas that gets thrown out by a dying star. The conditions in those nebulae are very similar to what the universe was like way back, like 100,000 years after the Big Bang.
So by studying those nebulae, we're basically like looking back in time to the universe's very first molecule.
Exactly. It's another piece of the puzzle that helps us understand how we went from simple atoms to those more complex molecules.
Okay, let's talk about the cosmic microwave background, the CMB. It's often called the afterglow of the Big Bang.
Right, so the CMB, it's this faint glow of microwave radiation that's everywhere in space, and is basically a snapshot of the universe as it was just 380,000 years after the Big Bang, when things finally cooled down enough for electrons to combine with protons and make neutral hydrogen atoms. And that's what made the universe transparent, allowing light to finally travel freely.
So it's like the universe's first baby picture.
I love that analogy. And this baby picture, it shows us these tiny temperature variations in the CMB. And those variations actually correspond to these density differences in the early universe.
And in those density differences, they're what eventually led to the formation of galaxies, right?
Exactly. The denser regions had slightly stronger gravity, so they pulled in more and more matter over time. And eventually, those clumps of matter, they became galaxies and clusters of galaxies. So the CMB, it gives us a ton of information about the early universe, like what it was made of and how it evolved.
Okay, so after the CMB, the universe entered this period called the Dark Ages. What happened during this mysterious era?
The Dark Ages, they lasted for hundreds of millions of years after the CMB. And they're called the Dark Ages because there were no stars yet, so the universe was basically dark. But a lot was happening behind the scenes. This is when dark matter, that mysterious stuff that we can't see directly, but we know it's there because of its gravity, it started to really shape the structure of the universe.
Right. Dark matter, it makes up like 85% of all the matter in the universe, but we can only see it through its gravitational effects.
Exactly. During the Dark Ages, dark matter started clumping together, forming this huge cosmic web of filaments and halos. And then normal matter, the stuff that makes up stars and galaxies, it got pulled into those dark matter clumps by gravity. And that's how the large-scale structure of the universe began to take shape.
So dark matter was like the scaffolding that galaxies were built on.
That's a great way to put it. Without dark matter, galaxies would form much slower, and they wouldn't be clustered together the way they are.
So we have the Dark Ages with dark matter kind of pulling the strings behind the scenes. What happened next?
Well, about 1 billion years after the Big Bang, the first stars and galaxies finally started to form, and they lit up the universe, bringing an end to the Dark Age. These early stars, they were massive, and they burned through their fuel really quickly, fusing hydrogen into helium and heavier elements. And when they exploded as supernovae, they spread those new elements all over, enriching the gas clouds that future stars and planets would be made from.
And then eventually our own solar system formed about 4.6 billion years ago, leading to the planet we call home and ultimately to us.
Exactly. It's just this incredible story that spans billions of years, involves all these amazing transformations.
But the story doesn't end there, right? The video mentioned this twist that like 5 or 6 billion years ago, something changed. And the expansion of the universe, it actually started to speed up.
You got it. This accelerated expansion, we think it's driven by something called dark energy, which is another big mystery in the universe. Dark energy is like this anti-gravity force pushing everything farther and farther apart.
So even though we've learned so much about the history of the universe, there are still these huge mysteries out there, like what dark matter and dark energy really are.
Absolutely. Those are some of the biggest questions in science, and they're driving a lot of research and exploration.
Well, this deep dive has been an incredible journey through space and time. We've explored the fiery birth of the universe, the creation of the first elements, the emergence of stars and galaxies, and we've even touched on some of those big mysteries that scientists are still trying to solve.
It's a story that never fails to inspire awe and wonder. It reminds us that we're part of something so much bigger than ourselves, something ancient and vast.
So next time you look up at the night sky, Remember, you're seeing billions of years of cosmic history unfolding before your eyes, a story written in the light of distant stars, a story whispered by the cosmic microwave background. And as we continue to explore and learn, who knows what other amazing discoveries await us. Thanks for joining us on this deep dive, and until next time, keep looking up.